Hello, my name is Tony Evelyn. I'm going to talk to you about one of the three experiments dedicated to geospatial. So the three experiments, one is about high resolution hybrid land cover mapping. The other one is about 3D field mapping for forest fire risk assessment. And the third one is the one we have been spending effort on, which is mapping water use footprints. And basically what we intend to do here is to assess the use of the water in crop fields through remote sensing images and with other databases such as, for example, SIGPAN. So for the three experiments, we follow the same schema. We've got on one side the data acquisition, remote sensing from two satellites from Copernicus constellation from the European Space Agency, and they also acquire data from LIDAR, from SIGPAN and others. And basically what we do with Cloud Bottom is that we generate spatial data, we process the data, and then we generate reports. And it's the same functioning for the three experiments dedicated to geospatial. Mapping water use footprint. Objective of this experiment is to want to assess the use of the water in specific areas. We want to measure differences in water consumption between crops and from official sources. We have to keep in mind that agriculture is a very important sector in Europe and more in Spain and even more in the region of Murcia. Here in Murcia, the agriculture is an economical engine, so it's really important for us to know when we have got to irrigate the crops, so basically when we've got to use the water. So the same schema as before, but this time dedicated to water use footprint. We acquire the data, satellites, other databases, we generate the reports. After we process and generate spatial data, we are able to estimate the water use in the field or the area we have been selected. The steps, inputs on the left side, all the data sources, and then the process that we can parallelize, and then what are the outputs, irrigated crops, changes in land use, crops, and crop conditions. And at the end, we are able to estimate the water consumption. So as part of this task 2.6, we are in charge of some smart cloud urban planning use case. We have been specifying the use case and we have been developing a few scripts, quite a lot of scripts, to download images from satellite, from LIDAR. So at the end, it was not requested. I mean, we didn't need to use this LIDAR data, but we have got the script. We also download different methodological data sources. We make some corrections on the images, radiometric, geometric. We do some filtering and topology. We select the zone we want to on, and then we calculate the NDVI, which is the normalized difference vegetation index, a simple graphical indicator that can be used to analyze remote sensing measurements. And basically, it is used to assess whether or not the target we are observing has got vegetation or not. Because NDVI is key for the overall process of what we are doing. Then we calculate the average per area and per month of the NDVI, we calculate some statistics, and finally, we evaporate transpiration, which is the one that is going to give us the water consumption. So scripts have been implemented in Python. We have been also developing some other tools like calculation in sequential time, RAM and space of all the scripts. We have been generating till now. We have been identifying which parallel task we can run in parallel thanks to the technology provided by Cloud. And finally, we have developed for this process, we are creating some notebooks for data preparation, for calculation of EI and calculation of the average. And the last step we have been implementing recently is the implementation, serverless implementation of the calculation of functional potential evapotranspiration. So all this notebook basically 6 notebooks with software inside, so data preparation, calculation of the DVI, average, memory profile, multi-process version of data preparation, and then some other tools for developers. The scripts are available in this GitHub that is just in front of you, and all of this has been developed from scratch, specifically for the Cloud Button project. So the infrastructure we've been using as framework Intel Core Machine for the acquisition of the data. We use as dataset the data, Sentinel-2, CPAR, methodological information, and information also from communities dedicated to irrigation. You have got here the owners of the data, type of access to the data, and the volume of the data. We have been focusing mainly on the region of Murcia, but the process we have been developing can be replicated everywhere else in Europe and in the world. Detectment and data processing the relational spatial database. Here we see what we've been working on and using. We select the region, we select the type of data, source data, Sentinel-2, CPAR, and then we're able to estimate the use of the water in the specific region we've been selecting before. So transition to servlet, which is the purpose of the Cloud Button. So we use two types of data partition, Sentinel-2 and MTN. So those two sources of data are used to estimate water consumption. Sentinel-2 works with so-called tiles, and MTN classifies areas, geographical areas, into sheets. And the processes, geoprocesses involved in this experiment take as input a tile, a sheet, and box, so that to calculate the water consumption of the region. We must take into account all the tile sheets that comprise this region. Therefore, to estimate the water consumption of a region, we can run geoprocesses in parallel for each tile of sheet, which is a really key aspect of the project, to run these geoprocesses in parallel, which saves a lot of time and a lot of resources. Here are all the processes that we've been developing. This is basically the workflow. We prepare the data, then we calculate all these parameters and DVI and average DVI. And most of it can be run in parallel, except the download from the data from satellite that cannot be analyzed, but the rest, yes. What are the next steps for this task 6, smart land and urban planning use case? We want to carry out all the transition to serverless, so, and move the code and the data to the test bed that has been prepared as part of the project. This is what we're going to do in the next part of period of the project. In terms of dissemination and exploitation, we are planning to attend the event in Madrid, a conference on intelligent environment, but because of coronavirus, that is possible. We plan to work together with the partners and prepare scientific exploitation of the results of the project, write a post on the questions in our web, in the web of the project. And because we are a company, we want to develop a minimum viable product, an MVP, from the NDVI calculation. We believe that we've got a really good business case, to sell the output and results of the project to potential customers involved in agriculture. So what we expect from Cloud Button is simple API, setting disk-based requirements, time efficiency, a huge computation power, and high quality on production results. Now I'm going to show you source code we'll be developing. So this is one of the notebooks, and particularly the one on water consumption. So here is the source code, and at the end we can see some results. we see here for the working with the IT environment. And we can see here some images that were being producing thanks to the cloud